Okay, in this video we shall continue the study of binary multiplication. So using Booth's algorithm. So in the previous video we have seen how does Booth's algorithm will going to reduce the number of additions in a particular number multiplication. So let us again just have a recap of that analysis. So assume that if I want to multiply plus 12 with plus 15, assume that okay, plus 15 happens to be the multiplier, and of course this 12 is the multiplicand. If I write the sign number of this plus 12, you can see this is the sign bit, which is 0 indicating positive number. This is a magnitude, and again this is plus 15, magnitude bit is 0 indicating it is positive. Then we have the magnitude as 111, 4 ones. If you actually do this, okay, 12 multiplied by 15, so this actually involves 4 additions and shift, because we know that okay, in order to get the complete output, so partial products have to be developed, which are done using the additions. So since we have all the multiplier bits are 111, so I need to have 4 additions and then corresponding shifting. This is what is required in a normal addition without Booth's multiplication, Booth's algorithm. Suppose if you go for Booth's algorithm, so what you're doing is you are appending a 0 and rewriting a recoded multiplier. So recoded multiplier is used to multiply your multiplicand. You can see your grouping, of course you are appending a 0 and then grouping it in twos. This is what is first grouping, second grouping, third grouping, all those things. And we know that for Booth's algorithm, if it is 0 0 0 1 1 0 1 1, so here you are simply doing the shift operation. Here also it is shift. Here it will be the multiplicand. Here you are adding the multiplicand shift, and it is adding the negative of the multiplicand and shift. So this what is 1 bar, indicating that you will be adding the negative of the multiplicand, and 1 means you are adding the multiplicand plus shift. So if you can see here, this is coded using Booth's algorithm, and then you end up with something like this, because this 1 0 happens to be 1 inverse, that is we'll be adding the negative of the multiplicand. Then it is, you can see 1 1, it is 0, again 1 1, it is 0, one more 1 1, it is 0. You can see you are simply doing the shift operation, and then you are having the final 1 here. It is because of the last combination, which is 0 1, which corresponds to 1. So if you basically see the difference between this and this, here you have actually 4 shift and add, add and shift. Here you are left out with only 2 additions, and the shiftings are there. In both the cases it is the 5 shift, but here it is the number of additions are drastically reduced for this particular case. This is in this way we can able to certainly reduce the number of additions, which will overall reduce the time that is required for multiplication. So you can see you are saving lot of addition times just in 4-bit number, binary number with a sign bit which happens to be 5-bit. Assume that you have a 32-bit number or 64-bit number or 128-bit number. You'll be saving lot of time in terms of multiplication of those numbers. So let us go to next concept, that is modified Booth's algorithm. So in this modified Booth's algorithm, instead of grouping the bits in twos, you group in terms of threes. So this is the table that indicates how the grouping is done. Suppose if you are grouping the numbers in threes, suppose if the group numbers, all the 3 bits are 0 0 0 or 1 1 1, you can see you'll be representing it by a 0. If the grouping is 0 0 1 or 0 1 0, so the corresponding modified Booth's algorithm multiplier would be 1, and of course it is 1 for this also. Then you can see if it is 0 1 1, so this happens to be 2. If it is 1 0 0, it is minus 2. If it is this and this, it is minus 1, and of course we have discussed this. So let us use this modified Booth's algorithm and write what is the corresponding modified multiplier by considering this Booth's algorithm. So we know that plus 12 happens to be same thing, which is now you have to do plus 12 into plus 15. So I know that plus 12 is 0 and 1 1 0 0, then plus 15 happens to be 0, and then this is my 15 number. So let me append with a 0. So I'll append with a 0. Let me start grouping in threes. So first let me just take this as the first 3 bit. When you're grouping the next 3 bit, you take the last MSB and then group it again. Now you can see this is also considered, this is common for both the first grouping as well as second grouping. Here you can see again, you start from here, you have only 2 bits. What you can do is you can add one more bit to make it a 3-bit number, Now you can see this is the grouping now. So grouping happens to be 110, in which case you can see 110 corresponds to, it is 1 minus, that is you'll be adding the negative of the multiplicand. Then you have 111. 111 actually corresponds to simply shifting operation. Next you have 001. 001 corresponds to addition of the multiplicand, simply addition of the multiplicand. Of course it is multiplied with 0 1 1 0 0, which is 12. So this is 12. This is what modified, of course this is a modified multiplier being decoded, or it is recoded using the modified Booth's algorithm. So now when I say it is minus, you have to add the negative of the multiplicand. So I need to write what is the code for, what is the binary equivalent of minus 12. So minus 12, I know that okay, the sign bit is 1. So I want to write the magnitude, and because we know that for magnitude 12 is 1100, its complement is 1100, it is 1's complement, and then plus 1. This is now 0 0 1 0. So I will represent minus 12 by sign bit as 1. The magnitude is this now, 0 1 0 0. This is now minus 12. If you actually see what is the first thing is, you are supposed to add the negative of the multiplicand. So that is minus 12 need to be added. So this is minus 12. The first bit itself is 0 0 1 0 1. As we discussed in the previous case also, because you need to have how many bits are there. Here it is 4, here it is 4 plus 1, that is you need to represent it by 9 bits. So this is the 9-bit representation. So let us just append this with 1, because whatever is your MSB, that need to be continued. The most important thing is that when you are doing the modified Booth's algorithm, here of course in the previous case also, while discussing this Booth's algorithm, once you add the multiplicand or its inverse or its negative number, we added and shifted by 1 bit. But here what happens is, once you added minus 12, the next, before you go for next addition, you have to leave 2 bits. The shifting has to be done by 2 bit. So I'm shifting it by 2 bit. Next it is 0. So 0 means you are not supposed to add any multiplicand. You have to shift it by simply 2 bits. Okay, I'm shifting it by another 2 bits. So this 2-bit shift is because you already added the negative of the multiplicand, which is minus 12, and you are extended the MSB to more number of bits. Then you are shifted, and then since the second recoded bit of your multiplier is 0, you are shifting by simply 2 bits. Next you have 1. 1 is nothing but, so I need to add the multiplicand as it is. Multiplicand is now 12. So I will add here 0 0 1 1. So this is my 12. Okay, let me just put the sign bit also here. This is 1. So this is my output. So my output is 0 0. Of course there's no question of shifting here because you don't have any more bits. Okay, this will be your answer. So this is 0 0 1 0. Then you have a 1 here, you have a 1 here. 1 plus 1 is 0 with a carry 1. It is now 3 ones, means it is a sum with a carry 1. Then it is 1 plus 1 is 0 with a carry 1. You can see now this is the 10th bit. You can discard this. Can you see now this is your final output, which is 1 2 3 4 5 6 7 8 9 bit. We said that okay, this will be represented using 9 bits. This is that 9-bit representation. So the number what you have is 0 1 0 1 1 0 1 0 0. So since this is a sign bit is 0 means it is positive. If you actually find what is the decimal or the values of these binary positions, so this happens to be 4 here, then it is 16 here, then it is 32 there, then it is 64, 128. So this is 128. So this happens to be 0 2 8. Okay, now this is 180. So of course we know that 12 into 15 happens to be plus 180. That's what is seen here. Basically what we are trying to do here is we actually wrote the sign number of 12 and sign number of 15, then we appended a 0 to the right side of the multiplier. We saw that now here one, of course, from this table, of course this table is fixed for any Booth's modified Booth's algorithm, as we have it as this as the table for the Booth's algorithm. So this is a table now. So if it is 0 0 0, of course as per this we'll write it. Since you have 1 1 0, the corresponding 1 1 0 you have it as -1, that is you'll be adding the negative of the multiplicand, or you are subtracting the multiplicand, or exactly the addition of the negative of the multiplicand, which is obtained here. -12 is 1 with the magnitude as take the 1's complement, again add 1, it will become 2's complement. This is the number. Then you can see 111 is no operation, simply shifting, and then we have it as 001, which is 1 here. So what we did was we added -12, we appended by few more ones, because whatever, if you want, of course, suppose if you don't put anything here or here, suppose if you consider as 0, you will end up with wrong answer. So make sure that whenever you are appending, the appending has to be done with same bit as you have it in your MSB. Then it is added and then shifted by 2 bit, and since it is 0 you are shifting by 2 bit, and then since it is 1 you are adding the multiplicand as it is, which is 12 with a sign bit, because when we find the answer it was coming out to be a positive number with 180 as the magnitude. So this way we can able to of course further reduce the number of course here you can see the number of shifts are 5, but here you will get the answer much more quickly. Of course maybe in this particular case you may think that okay, there are 2 additions, so there may be some cases where if you take larger number of bits, the number of additions and the shifting will be less compared to the compared to the Booth's algorithm in case of modified Booth's algorithm. This modified Booth's algorithm can also be used for, of course, any number. So maybe you can take one more example, something like let me multiply 14 with maybe -12. So -12, okay, I suppose if you want to write 12 is now actually it is 0, okay, or you can write it as 1100. Since you are looking at minus, let me just write -12 would be with magnitude, sorry, sign bit as 1, so you write it as 1100 with this as 1, this is 0010, so it is now 0100. So this is -12, so I want to have 14. Okay, 14 is as it is. So before we proceed, let us write its recoded multiplier. So I have 14. Okay, let me write it for -12. So -12 is actually 10100. You append a 0 to this to the right side and then start grouping in threes. So this is 3. You overlap the last MSB with this, and then you again overlap this with this. Okay, since you don't have one more bit, you can just add it. So as per the table, 000 corresponds to this is modified multiplier. So since 000 corresponds to, as we saw in this case, it is 000 corresponds to a recoded bit of 0, and then we have 010. Actually, if you can see, it is 010 corresponds to 1. You can take it as 1 there. This is now 1, and then you have again 010. So 010 again corresponds to 1. So you are lucky enough that okay, you are getting it as something like this. Now it is much more simpler. Of course, if you consider this even without modifying, you're getting almost the same number. Of course, don't worry about okay how many multipliers are there, how many additions are there. We're just simply trying to get concept of using the usage of modified Booth's algorithm. So 14 corresponds to 1 1 1 0, so with magnitude bit as so and so. Since you have it as 0, so you can simply write two zeros. Next you have 1. 1 is nothing but addition of this multiplicand as it is, that is 0 1 1 1. And of course you can have few more zeros. So this is the first shifting of 2 bit. Next shifting of 2 bits, then you have one more 1, which is now 0 1 1 1, and then you can have one more 1 here. So then you have of course 0 here. This is your sign bit. So you have 0 0, then this is 0, this is 1 1, 1 plus 1 is 1 with a carry 1 here. This is now 0 with a carry 1, 0 with a carry 1, 0 with a carry 1. So what do we have now? So this is now okay. Let us just try to find out do we went wrong anywhere or not. Let me just check it out. So since I have it as here, one thing we made a mistake here is that we have appended this with 1, which is wrong here. So why it is wrong means because I had this as minus 12. Whenever I'm appending, it has to be 1. It has to be 1. So you cannot append with a 0. So that's why I'm not getting it properly there. So when it is 110, so what is 110? 110 is actually minus 1. So if you can see here, 110 is minus 1. So here it's actually minus 1. That's why I'm ending with some issues here. So what is this minus 1? So minus 1 is actually minus 14. I hope you got this. Okay, you can see this answer is not tallying with, because you are not at all getting it as negative number, because this is the sign bit. Sign bit is coming out to be positive, which is not true in this case, which is you're supposed to get the sign bit as 1 here, because this is 1 2 3 4 5 6 7 8 9. This is the sign bit, because we made a wrong representation, wrong appending, so that's why we're not getting it properly. So of course we need to be very careful that okay, while appending it, so it should be the MSB one here. So in the previous case it was actually 0 itself. We actually appended it by 0 itself. Since it is negative, I need to append it by 1. So what is negative of the multiplicand? It is minus 14. So minus 14 is, this is sign bit number. 14 is actually 1110. Its complement is 1000. If I add one more, it is now 0100. Okay, now I will write minus 14 is 100010. Okay, let me just modify this. 0 1, this is now again 0, one more 0, and then this is 1. You can see this has to be appended by 1. This has to be appended by 1. Okay, let me rewrite this. You can see now this is 0, this is 0, this is 0, this is 1, this is 1. 1 plus 1 is 1 with a carry 1. This is 1, this is 0. You can see this is not there. You can see this is 1, and of course you have this as 1. See now, this is the number. So this is 1 2 3 4 5 6 7 8 9. Okay, this is my sign bit. So since this, of course you can discard all these things. So this is a sign bit number, so it's a negative number, so it is minus. And what is the magnitude of this? The magnitude of this is actually 2's complement of that, which is nothing but 1 1 1 0 0 0 0, plus 4 zeros and 1, then plus 1. So is it not 0 0 0 1 0 0 0 1? So this happens to be, this is 8 16 32 64. This is 128 plus 8, which is nothing but 136. So you can see this is minus 136. So we know that okay, 14 into 12 happens to be 130. Oh, it's not 130, 168. Okay, where did we went wrong? Let me just see. This is, we have it as 14 into 12 is 168. Okay, let me see. We have shifted by, this is 0. Okay, is 110 is equal to minus 1? Yes, this is minus 1. Is this 14 correct? This is 14. 14 is fine. This is 1 plus. Okay, 0, 1. Okay, this is fine. And then this is 0, 1, 0, 0, 1, 1. Okay, so this is 1. This is again 1. 1 plus. Oh, here we went again wrong here while adding it. So let me just clarify that. First, this is first 0, second 0, third 0, it is 1, then it is 1, 1 plus 1 is 0 with a carry 1 here, then it is 0, 1. So this is fine. This is now. Okay, is this fine now? So it is now 128 plus 128 plus 32 plus 32 plus 32. So this is 8 plus 16 plus 32 plus 128. 184. So where we are going wrong? This is 8. There is no 32. 8. It is 8 plus 16 plus 64 plus. Oh, sorry, this is negative number. I need to take its complement. Okay, this is a sign bit. Let me take the magnitude. Magnitude is actually 1 1 1 0 0 1 0 1 plus 1. It is 0 0 0 1 0 1 0 1. Okay, this is a number. So of course, this, since it is negative, you cannot take the magnitude as it is. If you want to take the magnitude, you need to take the 2's complement of this because it's a negative number. See, now this is 8. 8 plus 16, 32, and it is 128. You can see here, this is 8 and this is 16, 168. So we are having it as minus 168 is the number. So of course this was wrong here. Why it was wrong means we appended this by 0, and then okay, we were trying to find what is the magnitude from this itself, which is again wrong. If you want to really get the magnitude of a negative number, take the sign bit which is negative. If you want to know the magnitude of this one, it's actually the complement, 2's complement of this number. 2's complement of this is 1 complement plus 1, so this is 168. We know that okay, 14 into 12 is actually 168. Since it is negative, you are getting it as minus 168. So this way we can able to use this particular modified Booth's algorithm by appending it as 0 on the right, on the left hand side. On the right hand side it should be on the right hand side it should be 0. On the left hand side you have to append it using whatever is the MSB bit is there. Then you start grouping it threes. So using the table, you can just write the recoded multiplier, and then you can start adding or simply shifting. While shifting, so be careful, you have to shift it by 2 bits. So this way we can able to of course this is how you people usually end up with doing this. Of course it is good that okay, we are experiencing these type of mistakes even while learning. This is good that okay, you need not have to repeat such type of mistakes when you are asked to do it. Okay, thank you. We'll just see other type of multiplication in the coming classes.